Hi everyone, this is CHEM1001 and I'm going to just consider now the entropy of different phases of substances. So here's a picture of three phases: a solid, a liquid and a gas. Now it's pretty clear, I've told you before, that entropy is a measure of how dispersed or spread out the system is, either the mass or its energy. So the solid is the most compressed. It's not dispersed. The system is very ordered. The liquid is a little bit more random. The energy is a little bit more dispersed. The molecules are moving around, but not so much as a gas, where they're really moving all throughout the container. So what we can say is, and this is always true, the entropy of a solid is less than the entropy of a liquid, is less than the entropy of a gas. That's what this says here. And it has to do with how spread out or how voluminous a substance is. Sometimes we talk about that being more ordered. In this case, we can see that the solid is sort of arranged where the atoms stay in their positions but vibrate around there. In the liquid, they're not completely fixed, they can diffuse through. And in the gas, they're really diffusing very rapidly. Let's drill down and see how the entropy actually changes in more detail. And this is the graph here, showing how the entropy changes as you raise the temperature. I've shown here that the entropy at zero temperature, entropy at T equals 0, that's what this represents, that actually has a 0 value. That's called the third law of thermodynamics. We'll talk about that in a second. But what happens is, after we raise the temperature from absolute 0, assuming we could do it, we would add a little bit of heat to the substance and the temperature would go up. So entropy is heat. Entropy change is heat divided by temperature, so the entropy goes up. And we raise the temperature a bit more and the entropy goes up and up and up and up as we raise the temperature. In this case, we see that the entropy is flattening off. In other words, as we raise the temperature quite a bit, the entropy does not go up as fast as we expect. So there's a kind of flattening off here. Then something very remarkable happens. At this temperature, the entropy goes up vertically. What that means is the substance stays at the same temperature, and as we continue to add heat, the temperature doesn't change, but the entropy goes up. This is called a phase change. This, in fact, is the phase change between solid and liquid. At that temperature, it's called the melting temperature or the heat of fusion, T sub F. The temperature remains the same, provided you heat it up slowly enough, which is what we always assume in thermodynamics. We add the heat and the temperature stays constant, but some of the liquid is converted, some of the solid is converted to liquid, which has more entropy. So the entropy gradually goes up as all the solid is melted and finally it all becomes liquid. When the system is all liquid, it continues as it was for the solid. We can heat it up, entropy goes up. Heat it up, entropy goes up. Heat it up, entropy goes up. Heat it up. Finally, the liquid starts boiling. So we have another phase change here. Entropy goes up vertically from liquid to solid for the same reason. Now, this quantity here, if we're talking about 1 mole of substance, this would be the entropy change of vaporization. How much entropy it takes to the entropy difference between 1 mole of gas and 1 mole of liquid. And here we have the entropy difference between 1 mole of liquid and 1 mole of solid. Entropy change of melting or fusion. So we've noted how the entropy changes vertically at a phase change. In fact, that can be used to define a phase change in one sense. If the entropy goes up vertically, we have a phase change. That's the definition of a phase. Note that the entropy is 0, temperature 0. That's important because it allows us, if we didn't know that it was 0 at that point, we wouldn't really know what the entropy was at any temperature. We have to tie the entropy down to a particular value at a particular place, and that's entropy 0 at T equals 0. That's important. That's called the third law of thermodynamics. The entropy of all substances which are perfect crystals at 0 temperature is 0. Entropy of all perfect crystals substances is 0 at 0 Kelvin. No, all substances, even elements, have entropies. Even elements, provided the temperature is bigger than 0. And this allows us to tabulate entropies at temperatures greater than 0. Some special cases: a substance which is slightly disordered or dispersed at 0 Kelvin does not have a 0 entropy. When you cool something down, it doesn't always turn into a crystal. Even water, when you cool that down, it turns out that water will still have some residual disordered hydrogen bonds at 0 Kelvin, meaning to say that there is a slightly larger than 0 entropy at T equals 0. One of the reasons would be because the water actually is made up not of H2O, but maybe DOH or D2O, where D is deuterium. And the fact that we have a mixture means that we don't have a perfect substance.